Good morning, dear students. Uh, Let us take one more example on design of journal bearing. So, in the previous session, we have discussed about design of journal bearing used for a centrifugal pump. So, which is also we have presented as application-oriented problems where the diameter of the journal is not given. So, that is what the type 2 problems. Where with respect to the machinery, the bearing is to be designed. So we have to carry out all the necessary steps here. So take the one of the previous year question paper problem. So a journal bearing which is to be designed for a reciprocating compressor for a reciprocating compressor. So the compressor is given here for which the bearing is to be designed, and the operating speed is 1500 rpm. So which is n, and the bearing is to sustain a load of 4500 newton, so which is w, and this one is capital N, and diameter of the shaft that is given here. So in some of the cases this may not be given, so here it is given, so well and good, you can consider say 50 mm. Determine diameter of bearing, that is nothing but length of the bearing, and then viscosity of the oil, uh, viscosity of the oil to be used for the bearing, and suggest appropriate oil. So that is what the second one. And third one, coefficient of friction. Then fourth, we have to calculate heat generated. Fifth, we have to calculate heat dissipated, heat to be removed, and then Sommerfeld number. So these are the things which are to be carried out. That is nothing but we have to design the bearing by considering all the steps used in the general design procedure. Now we have to proceed with the actual procedure. So the very first step, we have to note down the given information which are noted here. N is 1500 rpm. So the small n, which is in rps, n divided by 60, that is 25 rps. Load acting on the bearing is 4500 newtons, and diameter of the shaft is 50 mm. Now we have to note down the recommended values for that particular machinery. So the machinery which is given here is a reciprocating compressor. So for the compressor, assume that the bearing is main bearing itself, and refer table number 15.7 from data handbook of page number 366. So note down all five important parameters which are recommended. So maximum pressure for that case is to be 1.8 Newton per mm square. Absolute viscosity is 0.0302 to 0.080 Newton second per meter square, and the bearing modulus, which is Zn by P. The minimum value of bearing modulus, that is Zn by P, is 4.36. That is the minimum value. So the value what we have to suggest, that should be more than 4.36, and C by R ratio is given here as 0.001, and L by D ratio is 1 to 2.2. So these are the parameters which are noted here. So the second step is to calculate the dimensions of the bearing, or which is also called as design of the bearing. So here diameter and the length of the bearing that are to be calculated, and also we have to fix the value of allowable pressure P, and also we have to fix the value of Z here, and also we have to get the value of C, that is the diameter clearance ratio, which is given here. So that is 0.001 multiplied by into r, that is radius of the bearing. So by using all these necessary information, we have to calculate the required, says d is known here. So with the help of that known d and known ratio, so 1 by 1.5 is the ratio that is selected, because here the value is 1 to 2. In between 1 to 2 we have to select that ratio, so 1.5 is selected. So 1.5 into d is 50 mm, so that value what we get for the length of the bearing as 75 mm. Pressure of the bearing, or allowable pressure in the bearing, is w divided by l into d, or w divided by 2rl. So 4500, L is 75, and D is 50 mm. So the pressure what we get is 1.2 Newton per mm square. So the maximum pressure that is allowed, or that is recommended here, is 1.8 megapascal, or Newton per meter square. So which is less than the maximum pressure itself. So the allowable pressure that can be accepted here. Then C by R ratio that is given as 0.001. So C is equal to 0.001 into 25, that is the radius. So the value of C radial clearance is 0.025 mm. So with this calculation, next we have to go for the third step, which is calculation of or determination of name, identification of name of the lubricant. So here, as per the Mahadevan data handbook, operating temperature that is not given, we have to assume it. So we have to refer figure number 15.3, where the operating temperature is given on the abscissa, uh, and the one more value that is on the ordinate, which is Zk, kinematic viscosity, which is in terms of centistoke. So this is given in on the ordinate of the right side of that particular figure. So with respect to 70 degrees centigrade, and with respect to the value of Zk, so Zk value that we have to calculate. So Zk value is given by Z divided by rho into 10 raised to 3. So what is rho? Rho is assumed here, that is zero point 0.9. So that is the standard value that is to be assumed for the liquid lubricant, zero point 0.9. So zero point 0.9 is a specific gravity. So if you want to get the mass density, which is to be divided by, which is to be used in the denominator of that equation, in terms of kg per meter cube or Newton per meter cube, so that is 1000. So multiply that specific gravity by 1000. What is that specific gravity? Specific gravity is defined as the ratio of mass density or weight density of the liquid or the fluid, divided by, or to divided by the mass density or weight density of the standard fluid. So specific gravity of the liquid lubricant is equal to mass density of the liquid lubricant divided by the mass density of the standard liquid is water. So 1000 is the multiplication factor mass density of water it is. So that the value of Zk what we get here is 4.44 into 10 raised to minus 5 meter square per second. What is Z? Z is noted from the noted in the first step itself, which is a recommended value 0.040 Newton second per meter square. So 4.44 into 10 raised to minus 5 meter square per second, the value what we got for the kinematic viscosity. Why this kinematic viscosity is to be calculated here? To refer figure number 15.3 to know the name of the oil. So Zk is equal to, in terms of centistroke, that we have to mention here, because in the graph the value is in centistroke. So the value what is obtained in meter square per second is to be divided by 10 raised to minus 6, or it is to be multiplied by 10 raised to plus 6. So that the value of Zk that is obtained here is 44.4 centistoke. So by using this 44.444 centistoke and operating temperature of 70 degrees centigrade, so the projection of these two points that will intersect at a particular curve, and the name of that curve or the line is H here by referring the figure. So H curve that is obtained here, so that is mentioned here. So for Zk value 44.4 CST, that is centistroke, and operating temperature of 70 degrees centigrade, by referring figure number 15.3 of page number 352, the curve which is selected is H. So therefore, with respect to the line H, what is the name of that oil? That is important. So that name of the oil, that is SAE 60, so which is referred from table number 15.1 of page number 363 of the data handbook. So for line H or curve H, the name of the oil lubricant is SAE 60. So this is what the identification of name of the oil in the third step. And whether the lubricant which is selected and have the value of Z which is 0.040, whether this oil which is selected is suitable for the functioning or not, that we have to check. So to check for that, we have to calculate the bearing modulus. What is bearing modulus? That is the equation which is given here as Zn by P. Z is absolute viscosity 0.040, N is RPM 1500 RPM divided by pressure which is calculated 1.2 Newton per mm square. So the value what we get here is 50. So, as per the fundamental rule, that the bearing modulus should be greater than the recommended value. So, here this value is 50, and the Zn by P, the recommended value is 4.36, minimum value it is. So, the calculated value is more than the given value. Hence, the thick film of lubrication or thick film lubrication that is possible. Hence, the oil which is selected is suitable. So this is what the third step. Next comes the fourth step. So in the before that fourth step, there is one more thing that is asked, that is the determination of coefficient of friction. That step is combined here itself in the fourth step. So heat generated is given by Fw into V. So V is velocity pi dn by 60 into 1000, so that we can easily calculate by knowing the values or by substituting the values of diameter of the shaft and RPM of the shaft. That is 3.93 we get here, 3.93 meter per second. And heat generated is obtained, or that equation is equation number 15.11a from page number 360 of the data handbook. And to calculate a coefficient of friction, since this is not a lightly loaded bearing, hence 15.4b, page number 353 equation that is to be used to calculate the coefficient of friction. And here the value of coefficient of friction what we got is 0.0182, and substitute that value of F in the equation of heat generated. So the heat generated value what we got here is 321.87 joules per second. So this is the amount of heat generated. Next, we have to calculate the heat dissipated. So heat dissipated is given by Kp into L into D into 10 raised to minus 6, equation number 15.11c, page number 360 and 361 of the data handbook. So Kp equation that is given separately in the data handbook. So here it is combined. So Kp is nothing but Tb minus Ta, which is rise in temperature. So the notation that can be used for this difference as T or delta T. That is the change in temperature, or directly the equation Tb minus Ta. Tb is bearing temperature, and Ta is ambient temperature, plus 18 whole square divided by 0.484. So this is what, again there is a notation which is given small k suffix p, or we can use this small k suffix 3 as the notation for that. That value is 0.484 ld into 10 raised to minus 6. 10 raised to minus 6 is the conversion factor to convert L into D product into meter square. Since bearing temperature is not given, so we have another equation, Tb minus Ta is equals to T naught minus Ta divided by 2. So T naught is 70 assumed, Ta is 25 degrees centigrade, that is also assumed, so that the rise in temperature is 22.5 degree centigrade. So after substituting all the values, what we get here, the value of Hd as 12.7 joules per second. So if we compare the values of Hg and Hd, so Hg is greater than Hd, hence artificial cooling is required here. So what is the amount of heat that is to be removed from the bearing? So that is nothing but the difference between Hg and Hd. So Hg minus Hd, that gives a value of 309.16 joules per second. So this is the amount of heat that is to be removed from the bearing surface. Hence artificial cooling is required. That is what the thing that is mentioned earlier. And then we have to go for another parameter, that is minimum film thickness, which is denoted by the notation H naught. So to calculate this, we have to use the equation minimum film thickness variable, that is equal to H naught by C. Equation number 15.7a, page number 356. So to calculate H naught by C, we have to refer the graph. So to refer that graph, we require the Sommerfeld number without side leakage. So equation number 15.6a of page number 354 of the data handbook. So S is equal to R by C whole square into Zn by P into 10 raised to minus 6. So here what we get that value as 50. So with respect, by referring figure number 15.9 of data handbook, page number 356, for the value of S equal to 50 and beta equal to 360 degrees centigrade, 360 degrees, that is full bearing, H naught by C is equal to 0.99. So therefore H naught is equal to 0.99 multiplied by the radial clearance. So that is 0.0248 mm. So H naught is equal to 0.0248 mm. Next comes the flow rate value. So flow rate Q is given by FLV, that is flow variable, multiplied by R into C, that is radius into radial clearance, multiplied by RPM into length of the bearing, equation number 15.8b, page number 358 of data handbook. So this is also here also we have to refer figure number 15.13 of page 358 of data handbook to note down the value of flow variable. So flow variable is noted with respect to S, that is Sommerfeld number 50, and bearing full bearing, that is 360 degrees beta value. So that the flow variable is 3.2. So substitute 3.2 in the equation, and all other values, that is radius, radial clearance, and RPM and length of the bearing. So the value what we get here is Q is equal to 2,25,000 mm cube per minute. So this is to be converted into meter cube per minute. So to convert the value into meter cube per second, so divide this value by 10 raised to 9, that is 1000 raised to 3, because 1000 mm is equal to 1 meter. So meter cube is required, so 1000 cube, and divide this value by 60 to convert meter minute into second. So that the answer what we get is 3.75 into 10 raised to minus 6 meter cube per second. And the last parameter, that is power loss. Power loss is nothing but the amount of heat generated during the lubrication or the friction, due to friction. So that is Fw into V divided by 1000. So the answer what we get here is 0.321 kilowatt. So this is what are the another kind of problem. So this is what the application oriented problem, where we have to apply all the necessary steps or general procedure steps used in the general procedure. So I hope you have followed the steps. Thank you.